Hello, Masahiro Tanaka from Fukuoka University, Japan. I'm happy to have an opportunity to present my recent research entitled Delayed Acceptance Markov chain Monte Carlo for Robust Bayesian Analysis. And this research is a contribution to the computation aspect of Bayesian statistics. Let me begin with the background of the research. In a standard Bayesian inference, a probabilistic model is used for the generating process and the corresponding likelihood function. And D denotes a set of observations with a sample size of n. Theta denotes a vector of unknown parameters. P of theta denotes the prior. Posterior density is proportional to the product of the likelihood and the prior. And because the posterior is generally intractable, we simulate random draws from the density using numerical techniques such as Markov chain Monte Carlo MCMC. A well-known shortcoming of standard Bayesian analysis is that it needs to fully specify a probabilistic model. For example, to estimate a linear regression, we must specify the distribution of the error, say the normality of U. However, this is a source of model misspecification. To deal with this problem, alternative quasi-Bayesian approaches have been proposed. They have different constructions of quasi-likelihood. This study considers two types of quasi-Bayesian approaches. In the first approach, a quasi-likelihood is based on an empirical risk function. For example, in a linear regression, the unknown parameter, the theta, can be estimated through an empirical risk function with quadratic losses. Here, a probabilistic assumption does not have to be imposed on the error, and thus theta can be estimated with more robustness. In this approach, a scaling parameter omega must be selected to calibrate the spread of the posterior. However, it is not a theoretically or computationally trivial problem. To tackle this problem, recently, Fraser and the others proposed a new approach that specifies a quasi-posterior as this. The main component is M bar, the mean of the gradient of loss functions. And W denotes a Weyl matrix. And this approach can provide the proper uncertainty quantification without selecting omega and some regularity condition. The second approach specifies a quasi-likelihood based on a generalized method of moments, GMM. In a GMM, a statistical problem is formulated through a set of moment conditions. For example, a linear regression can be estimated using a set of moment conditions like this. The quasi-likelihood is made of a GMM criterion. Evidently, this approach is closely related to the previous one. The biggest challenge in implementing Bayesian inference with these two quasi-posteriors is computational load. In fact, matrix W is computed as the inverse of a covariance matrix. The evaluation of the posterior is computationally expensive because of W. To the best of my knowledge, no studies have addressed this issue. In this study, I proposed a new algorithm based on a delayed acceptance Markov chain Monte Carlo, DA-MCMC. The proposed algorithm can be more computationally efficient than the standard MCMC because it can shorten the computation the inverse of W. A single cycle of DA-MCMC has two stages. In the first stage, after being generated a new state, the proposal is promoted to the second stage with a probability based on an approximate target density, which can be computed with locus. And this paper proposed to fix W to the current state to decrease the computational burden. In the second stage, the promoted proposal is accepted with probability based on the exact target density. This computational strategy has more steps than the standard one, but dramatically reduces the number of matrix inversions, decreasing the total computational cost. For demonstration, I compared the proposed algorithm with the standard one using synthetic data and real data. As synthetic data, I examined a linear regression with model misspecification. As a real dataset, I estimated an instrumental variable regression using a dataset from well-known paper of Asemoglu and others. The numerical performance of the algorithm was evaluated based on multi-dimensional effective sample size per second. As shown in this table, for the synthetic data, the proposed DA-MCMC is approximately 2 times more efficient than the standard MCMC. For the real data, the proposed algorithm also overwhelmed the standard one by a large margin. And finally, this figure compares the simulated posterior distribution of a key regression coefficient of the instrumental variable regression. The difference between the two was small. Therefore, using the proposed algorithm, DA-MCMC, we can simulate the same posterior distribution with lower computational cost. Thank you for attention.